Hello! We have been looking at mixed Nash equilibria and trying to find them in strategic games. For small games with 2 players and 2 strategies each, this is straightforward. However, in general, finding Nash equilibria is difficult. In this lecture, we will look at a special class of strategic games where an efficient algorithm exists for finding a Nash equilibrium in the game. And these are the 2-player zero-sum games. We begin with a definition. A strategic game is a zero-sum game if, for all the strategy profiles S, the sum of the utilities of all the players is 0. For example, matching pennies and rock, paper, scissors are both zero-sum games. We now focus on the 2-player case. For a 2-player zero-sum game, let S1 be 1 to m, and let S2 be 1 to n. We can define such a game with a payoff matrix A, which is an m by n matrix where the utility of player 1 with the strategy profile ij is aij, and the utility for player 2 is minus aij. Notice that we only need to define one matrix. The utility of one player is the negative of the utility of the other player. Take a look at this matrix, which is the payoff for player 1. This is A. And the payoff for player 2 is just the negative of that, which is minus A. Note that for a mixed strategy profile x1, x2, the utility for player 1 in this profile is also the negative of the utility for player 2 in this profile. We now try to find a mixed Nash equilibrium. This is going to be a min-maxing argument for finding such a Nash equilibrium. So given a strategy that we play, the opposing player will try to maximize their utility, which minimizes our own utility. Knowing how they will play, what can we do to maximize our own utility? We will look at each player's perspective for this argument and formulate an LP for each of them. We will also illustrate this process with our example above. So, from the player 1's perspective, suppose player 1 plays x1. They will expect player 2 to play from their best response. So player 2 will calculate their own expected utilities based on player 1's strategy. Recall that this is equal to the maximum utility of playing a pure strategy. In our example, the expected utility for player 2 for playing 1 is minus 3x11 plus 5x21. The expected utilities for player 2 for playing other pure strategies are listed here. Now, can you see how to write each of these expected utilities in terms of the matrix A and the vector x1? We see that each of these is just a dot product of x1 with the negative of the column of A corresponding to that strategy. So player 2's expected utility for playing pure strategy J is minus x1 transpose times A dot J, where A dot J is the jth column of A. Now recall that the utility of player 2's best response is equal to the maximum of these values. So in our example, we are looking for the maximum of these 3 expressions here. So that translates into max over all possible j minus x1 transpose A dot j. And this is equal to minus the minimum over all j x1 transpose times A dot j. So in our example, we are looking for minus the minimum of these 3 expressions negated. Now this is the utility for player 2. But it is a zero-sum game, so the utility for player 1 is just the minimum over all j of this expression here. And player 1 wants to maximize this value. So it wants to maximize this value subject to the sum of the probabilities is 1 and it is non-negative. Now this is not a linear program. The objective function is not linear. But we can turn it into a linear program. Can you see how to do that? We can use a new variable u1 to represent this minimum. As this is just the minimum of m different expressions, we can say that u1 is less than or equal to each of these expressions here. And since we are maximizing u1, the optimal solution would have u1 equal to the exact minimum of these expressions. We can write this out in the example here. The first 4 lines here tells us that u1 is going to be equal to the minimum of these 3 expressions. So this is the LP that player 1 would solve to maximize their own utility. We now look at player 2's perspective and apply a similar argument here. Suppose player 2 plays x2. Then, player 1 would play from their own best response. In our example here, player 1's best response has this utility, which is the maximum of these 2 expected utilities. Now, can you express this in terms of the matrix and the vector x2? The utility for player 1's best response is maximum over all I x2 transpose ai dot, where ai dot is the ith row of A. This is the utility for player 1, so the utility for player 2 is minus maximum of this expression. Player 2 wants to maximize this utility. And maximizing this is equivalent to minimizing the expression without the minus sign. So player 2 will minimize this maximum subject to the probability distributions for player 2. And we can do the same trick introducing a new variable u2, and this becomes minimize u2 subject to u2 is greater than or equal to each of these expressions here, and the remaining constraints. We can write this out for our example here. The first 3 lines will give us u2 is equal to the maximum of these 2 expressions. We will note that the objective function here is trying to minimize the negative of the utility for player 2. So this is the LP that player 2 would solve to maximize their own utility. Now there is a good reason why we go to great lengths to derive these 2 LPs. The punchline here and the main result is that the LPs for player 1 and player 2 are actually duals of each other. And we will ask you to verify this as an exercise. Now let's apply some duality theory. Both LPs are feasible. We can just take x1 and x2 to be any probability distributions, and u1 and u2 as the corresponding max and min values. Therefore, both of these have optimal solutions with the same objective value. Note that the objective value of player 1's LP is the utility for player 1, so the objective value of player 2's LP is the negative of the utility for player 2. And the way that we have set up the 2 LPs mean that the optimal solutions are best responses to each other, so they must form a Nash equilibrium. And we can find such a Nash equilibrium by solving it using simplex. There is a modified version of simplex that is provably polynomial time, so this can be found efficiently. So we have this theorem. Any two-player zero-sum game has a mixed Nash equilibrium, and this can be efficiently computed. If we solve our two LPs in our example, an optimal solution is, for player 1, 6/11 and 5/11, with U1 equals to minus 7 over 11. And for player 2, we have 3/11, 0, and 8/11, and U2 is minus 7 over 11. U1 is the utility for player 1, and minus U2 is the utility for player 2. And you can use support characterization to verify that these are best responses to each other, and therefore they form a Nash equilibrium. As a final note, we mentioned before that computing a Nash equilibrium in general is difficult. Even in the 3-player zero-sum game or 2-player general-sum game, no polynomial time algorithm is known. However, we do know that in every finite strategic game, a Nash equilibrium always exists. And we will see an outline of the proof in the next 2 lectures.